By 2035, the fastest way to become obsolete as a machine learning engineer may be to become exceptionally good at today's machine learning workflow. Training loops, architecture selection, hyperparameter tuning, and API wrappers are precisely what advanced AI systems are learning to automate. That does not eliminate the engineer, it moves engineering value. The scarce skill will not be producing a model. It will be proving that a learning system solves the right problem, on the right population, under real constraints, without creating a more expensive failure elsewhere. Start with problem formulation, because no optimizer can rescue a badly specified objective. A company may ask for a churn predictor, but prediction is not the decision. The decision is whom to contact, with which intervention, at what cost, under what capacity constraint, and with what risk of disturbing a customer who would have stayed. A high AUC can coexist with negative business value. The engineer of 2035 must define the action, outcome, unit of analysis, prediction horizon, counterfactual, loss function, and abstention policy. Ask whether the organization needs a forecast, ranking, causal effect estimate, anomaly detector, or optimization policy. These are not interchangeable. Correlation may identify who will leave. Causal reasoning asks whose behavior can be changed. That distinction can be worth more than another percentage point on a benchmark. Mathematical maturity will therefore survive every tool cycle. Operational command of probability, statistics, linear algebra, optimization, information theory, and causal inference. You should detect target leakage, selection bias, non-identifiability, confounding, label noise, and uncalibrated confidence. You should know why empirical risk can fall while deployment risk rises, why an average metric can hide catastrophic subgroup performance, and why uncertainty under distribution shift differs from uncertainty on an independent test set. When a model reports 0.9, ask whether outcomes occur roughly 90% of the time for comparable predictions in the population where the system now operates. In high-stakes settings, the model must also recognize insufficient evidence and defer. Selective prediction, conformal methods, uncertainty quantification, and decision-theoretic loss will matter more, not less. The next durable skill is data engineering with epistemic discipline. Models will become easier to obtain. Trustworthy evidence will not. The engineer must know where each signal came from, what process produced it, what permission governs it, how it changed, and what failure it can introduce. That makes temporal joins, point-in-time correctness, schema evolution, entity resolution, data contracts, lineage, versioning, and privacy core ML skills. A feature calculated 1 hour after the decision can make an offline model look brilliant and make production useless. A label can be consistent, yet measure institutional behavior rather than reality. Research on data cascades shows how neglected data work compounds into downstream harm. In 2035, elite engineers will treat a dataset as a measured artifact with provenance and limitations, not as a clean table waiting for a model. Systems thinking comes next. Google's research on hidden ML technical debt showed that feedback loops, undeclared consumers, entangled features, and unstable dependencies make the model only a small part of the production problem. Foundation models multiply those risks. A real system may combine retrieval, re-ranking, memory, caches, tool calls, policy engines, human review, and models owned by several providers. Change one component, and the error distribution of the whole system can move. The engineer of 2035 must reason about a graph of coupled, stateful components, not a notebook containing weights. That requires typed interfaces, tests, observability, distributed systems, concurrency, accelerators, memory hierarchy, networking, and failure recovery. You must understand generated code, trace a request across services, reproduce an artifact, roll back a release, and design idempotent recovery when an agent repeats an action. Learn enough hardware to reason about memory bandwidth, communication overhead, and energy. Learn enough optimization to choose among quantization, distillation, sparsity, batching, caching, and smaller specialist models. The right model is not the largest one the budget permits. It is the smallest system that satisfies quality, latency, resilience, privacy, and cost. Use a metric I call cost per trustworthy outcome. Do not divide infrastructure cost by model calls. Divide total operating cost by correct, useful, and policy-compliant outcomes. Count retrieval, retries, human escalation, incident response, energy, and consequential errors. A cheap model requiring repeated calls and manual repair may be expensive. An accurate model with excessive latency may destroy the workflow. This metric forces ML, product design, and economics into the same equation. Evaluation engineering may become one of the decade's most valuable specializations. The 2026 Stanford AI Index describes a widening gap between rapidly advancing capability and our ability to measure and manage it. Static benchmark scores cannot validate systems that plan, call tools, and change their environment. You will need task-specific evaluation sets, meaningful non-ML baselines, slice analysis, metamorphic tests, counterfactual cases, red teams, shadow deployments, and online experiments. Measure calibration, tail risk, latency, recovery, resource use, and abstention cost not only average accuracy. For an agent, evaluate the trajectory. Did it choose an authorized tool? Expose sensitive context? Recover after failure? Stop when evidence changed? Reach the correct answer through a dangerous path? A study of agents in production found that only 39% of surveyed teams compared their systems with a non-agentic baseline. Autonomy is not a benefit unless it defeats a simpler workflow after reliability and supervision costs are counted. Give every important system a failure budget and an evidence map. The failure budget specifies which errors are tolerable, for whom, how often, and at what severity. The evidence map connects every major claim accuracy, fairness, robustness, security, and latency to a test, dataset, owner, threshold, and monitoring signal. If a team says the system is safe, ask which measurable result would falsify that sentence. This turns evaluation from a final gate into an executable scientific argument. Security engineering for stochastic systems is equally durable. The attack surface now includes training data, model artifacts, prompts, retrieval stores, tools, memory, and feedback channels. NIST's adversarial ML taxonomy covers evasion, poisoning, privacy attacks, and misuse across the lifecycle. Agents add prompt injection, excessive permissions, confused deputy behavior, and multi-step attacks whose individual actions appear harmless. Learn threat modeling, least privilege, sandboxing, signed artifacts, secret isolation, input provenance, and immutable audit trails. Never give a probabilistic component authority merely because it speaks fluently. Put deterministic controls around irreversible actions, separate planning from permission, and make dangerous operations fail closed. Governance must also become architecture. The EU AI Act emphasizes risk management, data governance, logging, documentation, human oversight, robustness, and cybersecurity, while the NIST AI Risk Management Framework organizes work around govern, map, measure, and manage. An engineer who treats these ideas as paperwork will lose value to one who implements them. Human oversight requires useful intervention points, not a decorative approval button. Accountability requires reconstructing which data, model, prompt, policy, and tool state produced an outcome. The best teams will generate compliance evidence through delivery pipelines instead of assembling it after deployment. Domain knowledge is another lasting advantage. Medicine, semiconductor manufacturing, finance, logistics, and energy have different causal structures, safety limits, and definitions of error. A general model may know the vocabulary. An embedded engineer knows which proxy is dangerous, which measurement is delayed, which exception is normal, and which failure could stop a factory or injure a patient. Build a T-shaped profile. Deep expertise in one consequential domain, supported by broad competence in learning theory, data, systems, evaluation, and risk. Generic model builders will be plentiful. Engineers who connect a domain's physical or institutional reality to a verifiable computational system will remain scarce. And yes, AI-assisted coding will be mandatory, but the valuable skill is not prompting for more code. It is designing a verification loop around machine-generated work. Write the specification first. define invariants, generate adversarial tests, inspect dependencies, benchmark the baseline, and demand reproducible evidence. Treat AI output as an untrusted but extremely capable contribution. Let machines expand the search space. Make humans own the acceptance criteria. Clear technical writing also matters, because specifications, data documentation, model cards, and incident reports allow reasoning to survive across people and time. So, how should you prepare now? Build fewer demos and more complete systems. Take one real problem from raw, imperfect data to monitored deployment. Establish a non-ML baseline. Document provenance. Test temporal leakage. Measure calibration and subgroup errors. Constrain latency and cost. Simulate distribution shift. Attack the system. Add abstention, human escalation, and rollback. Then write a failure report before the failure occurs. Repeat in a domain you care about. Read papers, but reproduce claims. Learn frameworks, but invest more heavily in principles. Once every quarter, remove the fashionable model from a project and ask whether rules, retrieval, optimization, or a better process solve it more reliably. Knowing when not to use machine learning is a mark of maturity. By 2035, machines may generate most models and much of the surrounding code. They will not eliminate engineering, they will expose imitation engineering. The profession will belong to people who can frame the decision, establish the evidence, design the constraints, secure the interfaces, quantify uncertainty, and accept responsibility for the outcome. Do not build your career around being the person who knows where to call fit. Build it around being the person who knows what must be true before any system deserves to act. In the next era of machine learning, intelligence will be abundant. Judgment under evidence will be the scarce technology.